Good afternoon, and welcome to the applications of AFM for Semiconductor and 2D Materials Research event. My name is Tiffany Willoughby, Research Education Programs and Outreach Manager in the Office of Research at the University of Texas at Dallas. I will be your moderator. Joining me today is Mayur Savla. Mayur is the Director of Technical Sales for Asylum Research, focused on AFM metrology for industrial and research applications. He has over 15 years of AFM experience. He has a bachelor's in electrical engineering and a master's in biomedical engineering from The Ohio State University. Please join me in welcoming Mayur Savla. Mayur, welcome.
Thank you. Good morning, everyone. I'm going to talk today about AFM, specifically applications of AFM for semiconductor and 2D materials research. And I'm going to break my talk down into five smaller topics. We will talk about applications of AFM for roughness measurements. We will talk about step height measurements. We will talk about what are the other types of measurements you can do with AFM that go beyond surface topography. We will talk about applications of AFM for 2D materials research. And then the last section will be about the new instrument that UT Dallas just acquired from our company, which is called the JupiterXR. And feel free to ask questions at the end. I'll be here to answer all the questions. Let's get started. So roughness measurements have been around for a long time. Roughness measurements were started in the 1930s when stylus profilers were first invented. And the concept is extremely simple. You use a sharp tip that scans over the surface, and it gives you a measurement of the surface profile. And as you look at the image on the top, you notice that in this sample, what you have is you have a surface that has a profile. The surface also has a waviness, and it has a microscale roughness. So when we talk about roughness, we are talking about the third one, which is the higher frequency changes in the surface. So now any real world surface will likely have all three components. It will have a profile, it will have a waviness, and it will have a roughness. And microscale roughness is a very important parameter that is measured across almost all industries. Whether you are designing an aircraft coating or paint on a car, or you are in the semiconductor industry and you are polishing wafers so that they perform as per spec. Controlling the roughness is important to minimize friction when there are moving parts, and it is important for semiconductor applications to make sure your deposition and etch processes perform as expected. Now, atomic force microscopy is able to measure roughness at the nanometer and the angstrom scale. So the examples at the bottom show an average roughness of 1.3 angstrom for the left image. For the one in the center, that is an epitaxial silicon wafer, where you can see the atomic planes of the epitaxial silicon with a surface roughness of 0.9 angstrom. And on the right hand side, we have an example where we have measured the surface roughness of a 2D material, which is only 0.43 angstrom. So you can see that from the 1930s, where the roughness measurements were in the millimeter scale, to 2020, we can now measure accurately roughness on things down to the sub-angstrom scale or the picometer scale. So things have come a long way. And once again, the instrument that your university just acquired is able to make these types of measurements. Now, there are different metrology techniques that are used to do surface roughness or surface dimensional measurements. I'm going to compare the three most popular surface characterization tools and explain to you, when you will want to use what instrument, assuming you have access to all three of the instruments. So 3D optical profilers, stylus profilers, and AFM. So 3D optical profilers are a non-contact metrology technique that use an objective and they take a picture just like a standard microscope. The main difference is in a 3D optical profiler, you get a three-dimensional profile of the surface. In a stylus profiler, you have a tip that just scans across the surface in a straight line. And as it scans across the surface, when your surface roughness changes, the tip picks up the profile of the surface. And in AFM, many of you may be familiar. If you're not, I'll explain, very briefly. The way AFMs work is you scan on the surface line by line in a raster pattern. And as you scan the surface, the sharp AFM tip is able to track the surface roughness and you get an image of the surface profile. So when you compare the vertical resolution, AFM is often an order of magnitude better than any other technique that is out there. So it's a really nice technique that gives you great results with the highest possible resolution. The vertical range of AFM is less than the other techniques. So 3D optical profiler may allow you to measure very tall samples. Stylus profilers can measure samples up to a millimeter. And AFMs typically have a range of around 10 to 15 micron. The instrument, once again, that UT Dallas has, the Jupiter, is a 12 micron Z range. The lateral resolution is where AFMs are significantly better, sometimes by over 1,000 times better than any other technique. Now, it's quite obvious that in any optical technique, your resolution is going to be limited by the wavelength of the light that is used for the measurement. In case of a stylus profiler, your resolution is limited by the radius of your stylus tip. And in case of AFM, your resolution is also limited by the radius of your tip. But AFM tips can be very, very sharp. Sometimes they are sharper than even 1 nanometer. So you can get some outstanding lateral resolution with AFM. The lateral range of the measurements in an AFM is up to 100 microns. In other techniques, it can be a lot bigger. Now, the measurement time is one of the areas where people feel like taking AFM measurements is like watching grass grow. But things have changed. AFMs have become a lot faster and a lot easier to use. And it no longer takes, tens of minutes or hours to take AFM measurements. It's actually become a relatively fast instrument. So now you can acquire a nice image in just a couple of minutes. But once again, compared to an optical profilometer that can take the entire image by just a flash like a picture, which only takes a couple of seconds, AFMs are still slower compared to those techniques. So what is the advantage of using an AFM? It is by far the highest resolution technique that's out there. And the other advantage is because it involves an AFM tip interacting with the surface, you can measure lots of interesting surface properties. So surface properties, the examples are changes in conductivity of the surface or changes in mechanical properties like how soft or how stiff or how hard a certain region is. So those would be the main advantages. But is AFM the right technique every time? Not necessarily. So if you're looking to get a quick picture of your sample and you only care about micron scale resolution, you're better off with some of the other techniques. Also, if you need to make a very large view of your sample, you are better off with other techniques. But AFM is best for high resolution measurements that require highest precision, highest accuracy, and if you're interested in other surface properties. Now I'm going to give you some tips about how to use an AFM. Since every one of you have joined an AFM based seminar, I assume that you are interested in AFM. So I'm going to give you some tips on how to select probes, what to watch out for in collecting the best measurements. So the first and the most important thing in AFM is the radius of the tip. So the radius of the tip decides how well you're going to measure the surface or with what fidelity. So you need to make sure your tip is sharp enough to actually measure the surface. The example on the right shows what happens when your tip is too blunt. So if you look at the bottom image on the right hand side, we have a surface profile that is not being measured accurately because your tip is too blunt. The example in the center, a typical tip gives you more or less the right answer, but a super sharp tip gives you the most accurate measurement of the surface. So what you should try to do is make sure you are consistent with the type of probe you use if you are comparing different samples. And also, it would be a good idea to make a measurement on the sample, the same sample first and the last time to make sure your tip has not changed as you're measuring different samples. So the two images on the left is an example of a measurement done on a Jupiter AFM where we took 1,000 measurements on the sample and the roughness did not change over time. So that's an example of a high quality AFM measurement where the tip does not change with time. Now, what are the other factors to keep in mind? So how well the tip is tracking the surface is very important. So in AFM, it would be great to get results as fast as possible, but you have to make sure that you're tracking the surface well. And the example on top shows what happens if you scan too fast and you don't track the surface. Going from a 40 Hz line rate where the average roughness was measured to be 234 picometers, going down to 1 Hz line rate where the average roughness was measured to be 298 picometers, you find that the image also looks sharper and the image on the right has better tracking, so the results are more accurate. So you want to choose a scan rate that gives you the most accurate results, and the choice depends upon how rough your sample is and how sharp your tip is. So there are multiple things to keep in mind, but it's important to make sure you track your surface well. The other thing to keep in mind is the gain of the feedback loop. So when you go and receive AFM training from the staff at UT Dallas Clean Room facility, they are going to explain to you how an AFM works. And there is a parameter called gain, which is part of a feedback loop. And if you set the gain of the AFM to be too low, then you will not track the surface. And if you don't track the surface, your numbers are going to be inaccurate. So you need to make sure that the gains are set up correctly. The other thing to keep in mind is AFM measurements involve measuring a certain number of pixels in your image. So we count the pixels from left to right, and we count the number of lines from top to bottom. So frequently we would refer to an AFM image as say 512 by 512 or 256 by 256. And what that means is how many points do I save along a line and how many lines I save in the image. So if you take a look at the series of images from left to right, this is the same exact location imaged with a different number of pixels. And it's really obvious that on the left hand side, the image is washed out and you are not saving enough points to get an accurate reproduction of your surface. So if you take a look at the blue line in the graph at the bottom, that blue line is from the image where we only saved 64 pixels and we are undersampling the surface, which means that even though the surface profile is changing more than what we are measuring, we are only saving a few points. So the number that you get is inaccurate. So the summary of this slide is that make sure you save enough number of pixels in the image. But once you are saving enough number of pixels, by just increasing the number of pixels, you don't really get any benefit. It just means that you have longer imaging times. So for many measurements where you're doing say 1 or 2 micron scan sizes, 500 pixels is usually more than enough. And the way to make a choice would be to divide the total area that you're imaging by the number of pixels. That will give you the pixel resolution. And once you know the pixel resolution, You have to think about, is that enough for my work? And if it's not, then you can increase it. If it's too much, then you can reduce it and save time in the measurement. The other thing to keep in mind is how large of a scan size you're going to choose for your sample. And the simple way to think about this is, if you have a very rough sample where your topography is changing too much, you probably want to do a larger scan size to make sure you capture all the changes in your surface. On the other hand, if you have a smooth surface that is more homogeneous, you can get away with making a smaller measurement. So the example that is shown on the screen, the graph on the top shows a surface that has different kinds of profile. So if you only made a measurement of the blue box that is shown on the left, you get a view of the surface where you think, OK, the roughness is what's shown in the blue box. And if you make a measurement that is shown all the way on the right hand side of an even smaller region of the sample, then you would think that the roughness of the sample is what's shown in the box on the right. Now the question is, which of these three measurements are correct? And the answer is all three are correct at different length scales. The question is really to the user, what is important for you? Is it important to understand the entire surface profile, or it is important to understand the surface profile in very small sections at the nanoscale? So we will now talk about step height measurements. So we talked about roughness measurements. Roughness measurements is probably the most popular thing people do with AFM. And the second most popular thing people do with measurement is measure step height or topography. And in order to understand step height measurements and how they work, I'm going to use a cartoon that explains how an AFM actually scans the surface and how does an AFM feedback loop work. So what you see on the screen is a sharp tip, and below the tip is a sample with a step height. And this tip is going to scan the surface. As the tip scans the surface, the AFM involves a laser that shines on the back of the cantilever, and this laser is then reflected back into a detector. And as your tip taps on the surface in tapping mode AFM, where the tip is oscillating on the surface, you get a measurement of the height of the sample. So I'm going to play through the different slides into a small animation. So what you see here is the tip is tapping on the surface, and as the tip taps on the surface, the detector measures the response of the tip in the form of a sine wave. Now, when your tip goes over a different part of the sample that's taller, now there is less room between the tip and the sample, and the amplitude of oscillation of the probe becomes smaller. So now you have a smaller amplitude of oscillation. And in an AFM, we have a feedback loop that measures this change in amplitude. And AFMs have a Z piezo that respond to the change in the amplitude. And when the amplitude is smaller than the desired amplitude, which is often called the set point, the Z piezo retracts the tip away from the surface and finally brings the amplitude back to the desired value. So once again, I'm going to play the movie backwards, and you will find that we start by tracking the bottom part of the sample. As we go above, the amplitude becomes smaller, and the feedback loop pulls the scanner back, and now your amplitude returns back to the set point value. Now, if you notice, there are two things I have mentioned on top. One is the Z piezo and one is the Z sensor. So what is the difference between a Z piezo and a Z sensor? So a Z piezo is a piezo that responds to a changing voltage that comes from the feedback loop, and it can bring the tip closer to the sample or away from the sample. And the Z sensor is something that is an independent observer. It is a new feature in AFMs that allows you to accurately measure the surface topography, and it is not part of the feedback loop. Now, the question is, there are two different measurements that are available in the instrument. we have the height measurement and we have a Z sensor measurement. And as a user of the AFM, how do you select which of the two channels is going to be the appropriate channel for your measurement? And the answer is it depends. On the micron scale, the sensor is more linear and the data you get from the Z sensor is going to give you a more accurate measurement. And at the nanometer or the sub-nanometer scale, the height data has lower noise and it gives you a more precise measurements. So I'm going to use an example to demonstrate that. So say you have a block, you have a surface, which is this brown thing at the bottom, and I have a giant cube that sits on the surface. And on top of this giant cube, I have a tiny little cube that sits on top. Now, if I want to measure the height of this large cube, the Z sensor is going to give me a more accurate measurement because of the linearity of the Z sensor over the entire range. So in this case, I would want to select the Z sensor because the Z sensor gives me a more accurate answer for the height. And the Z sensor gave me a height of 5.76 microns. The Z piezo gave me a height of 4.81 microns. I would trust the numbers from the Z sensor because it's more linear. Now, on the other hand, let's say we want to measure that tiny little cube on top. Now, when the cube is say 40 nanometers, both the Z sensor and the height are going to give me a pretty accurate number. You notice that the level of uncertainty, which is the plus or minus 0.04 nanometers on the height sensor, is larger than the one on the height. So I would say in the height or the height sensor will both give you a pretty accurate measurement. What if there was another tiny cube on top of this small blue cube and I wanted to measure the height of that one? So at the nanometer or the sub nanometer scale, say the height was 3.6 angstrom. Now the noise in the sensor measurement becomes important. So a 3.6 angstrom step height measured with a 0.4 angstrom noise will have more uncertainty in the measurement than a 3.6 angstrom measured from the height channel measured with only a 0.1% uncertainty. So the take-home message from these slides is that use the height sensor when you're measuring things that are more than 100 nanometers and use the height channel for measuring things that are less than 100 nanometers, especially if you're measuring things that are only a few atomic layers. OK, so moving on, let's talk about what are the other types of measurements that you can get from an AFM. Now remember, an AFM measurement involves a physical tip touching the sample. Now, when you have a tip touching the sample, there is a lot of interesting interaction that happens at the nanoscale, and you can take advantage of these interactions and measure material properties. So the first example I'm going to give you is a technique called scanning Kelvin probe microscopy. Now, just a quick footnote, there are different names given to this technique. Scanning Kelvin probe microscopy is the same as Kelvin probe force microscopy, is the same as Kelvin probe microscopy, and it is also known as surface potential microscopy. So this technique allows you to map charges on the surface. It allows you to map the differences in work function between, say, metals and semiconductors. And it can be used for things like semiconductor measurements where you see trapped charges or surface polarization. It can be used to study active devices. It can be used to study, corrosion that happens on the sample. So I'm going to give you an example of a measurement we did with a research group at Stanford that works on 2D materials. So this research group worked on developing a device that uses a carbon nanotube that can trigger an insulator to metal transition in vanadium oxide. And they are trying to make nanoscale devices that can work at lower power. Now, what they found is when they added a carbon nanotube in their device, they were able to make the transition from an insulator to a metal at a lower voltage. And this measurement we were able to observe at the nanoscale using Kelvin probe force microscopy. So let me explain what's going on here. So the measurement on top, the left image is of surface topography, and the images on the right is of surface potential. So we are applying different voltages onto the surface. So Vs is the surface voltage. So we start with 0 volts, we go to 40 volts, and then we go to 52 volts. And what we find is to change the sample from an insulating phase to a metallic phase, you have to apply as high as 52 volts when it's just the native surface of vanadium oxide in this nanoscale device. On the other hand, when the research group added a carbon nanotube onto the device, what we find is that the carbon nanotube creates a local electric field on the sample. And as we increase the surface voltage from 0 volts to 15 volts to 22 volts, we see a transition from an insulating phase to a metallic phase at only 22 volts. So without a nanotube, it took 52 volts to get to the metallic phase, and with a nanotube, it took 22 volts. Now, what is the role of AFM in this research study? What the researchers were able to do is observe at the nanoscale an in situ experiment where they can now study how their device performs and compare these results done with bulk electrical characterization. But at the nanoscale, you can see exactly the charge profile that the carbon nanotube creates on the surface. And this was a really exciting result for this research group. And these are the sorts of things you can do with surface potential microscopy. You can measure surface charges. You can measure differences in work function on different parts of your sample. The other measurement that is often used for semiconductor and 2D materials research is called conductive AFM. And the idea is really straightforward, but the applications are really awesome. So in conductive AFM, we apply a DC bias between the tip and the sample. And when you apply a bias between the tip and the sample and you scan the surface, you can get a map of the current that goes from tip into the sample or from the sample into the tip, depending on the direction of the bias. And this gives you a local map of conductivity on the sample. So if you compare this with other bulk scale electrical characterization techniques, this has much higher resolution and it is much easier to use compared to nanoprobing or using a probe station. So you can land the tip on your sample and very quickly do a 2-point electrical measurement. The other thing that's nice about conductive AFM is you can also hold the tip constant at a fixed point on the surface and do IV measurements just like a probe station. And by doing IV measurement, you can actually study from point to point the effect of voltages at the nanoscale on your sample. So this technique is used to measure charge transport in nanostructures. It is used in renewable energy research in photovoltaics by studying the effect of light and seeing the generation of charge carriers. It is used for characterization of defects in dielectrics. In the industry, it is used for failure analysis. So companies like Texas Instruments have several AFMs that are used for studying the failure modes of their devices. Other semiconductor companies like Intel and TSMC, they may have more than 10 or 20 AFMs in a lab that are doing conductive AFM all day long. So as a student at UT Dallas using AFM, learning AFM and also conductive AFM would be a sought after skill set as you go and transition into the industry. So what do some of these measurements look like? So this example is a surface that has several transistors. So each of these white dots is a transistor, and an AFM tip can go and land on each point on this surface and perform a current versus voltage measurement. This IV measurement will give you whether these devices are working well or not. And after taking this measurement, we can characterize the transistors into three types. One is an active device, the other could be a leaky device, another could be an open device. And we can assign a color code to these devices. So an active device is something that has a regular profile in the IV map. Those are characterized as green in the yield map. The ones that show a short are characterized as red, and the ones that have an open are characterized as yellow. So by doing IV measurement, you are able to get a yield map of many transistors on an IC. And this measurement is super useful for people studying semiconductor devices, and it's also frequently used in the industry. Now, we won't have time today to go through every single AFM mode. I would encourage you to talk to the new owners of the AFM at UT Dallas Cleanroom facility and ask them what are the different modes available on the instrument. And you will find that a lot of these modes are super interesting for different types of research. This seminar is about 2D materials and semiconductor, but AFMs can be used for doing polymer research, biological research. There is a lot of different kinds of things that you should be able to do with AFM. And you can also reach out to us and we would be happy to help you design your experiments to study your surface properties at the nanoscale. Let's talk more about 2D materials. 2D materials is a class of materials where you have ultra thin layers of different materials like graphene, hexagonal boron nitride that offer properties that are different from the bulk material. So bulk carbon has different properties than a single sheet of graphene. And over the last 10 or 20 years, this field of research has really experienced exponential growth. And 2D materials offer an exciting opportunity to make transistors smaller and to create low power devices, faster devices. So the field of 2D materials research is very exciting. And the good news for AFM is that most of the characterization you need to do for 2D materials can be done on AFM. So what are the type of things that people are working on these days? So one of the hot topics in the 2D materials community is something called as twisted bilayer graphene. Now I won't get into too many details of how to make a twisted bilayer graphene. I'll just explain that it involves two layers of graphene and carefully controlling the angle between the first layer and the second layer. And a few years ago, a discovery was made that by controlling this angle and putting the second layer of graphene on top of the first layer at a specific angle called the magic angle, you can get superconductivity between the two layers of graphene. And it's a phenomenal discovery, and it could potentially transform how we transmit electricity, how we make devices, how much energy is consumed in devices. It could really change almost any area of science by getting superconductivity at room temperature. And this is simply achieved by changing the twist angle between the first and the second layer of graphene. So it's a very interesting area of research. And AFM can allow you to see what was the angle between the two layers of graphene. Turns out it's actually pretty hard to know what that angle exactly is. Now, the good news is that when you place one layer of graphene on top of the other, because of the lattice spacing, you end up forming something called a moire pattern. Moire pattern in this image in the center is these bright and dark dots that you see on the surface. And as you change the angle, the moire pattern is going to change. And AFMs are very well suited to make these moire pattern measurements in both topography as well as in other channels like conductive AFM current and piezo response microscopy. So if you're working on 2D materials and you would like to measure the moire pattern spacing in your device, definitely reach out to the AFM group or reach out to us and we will guide you through how to make these measurements. Let's talk about an example. So the example over here is two different 2D materials stacked on top of each other. So in this case, molecular beam epitaxy was used to grow graphene on top of hexagonal boron nitride. And because the spacing of the atoms is different in hexagonal boron nitride versus graphene, what you find is the Moiré pattern changes. And you will see that the Moiré pattern is visible on the left side of the crack and on the right side of the crack based on the lattice mismatch. And the variable periodicity represents the strain-induced spatial variation in the lattice constant. So if I zoom in and I save higher resolution AFM images at location B, C, and D, you will find that the spacing of the atoms is different. And so the lattice orientation of the graphene is different in the three places, which is what results in the different spacing in the Moiré pattern. So this is a really nice way to figure out what is the orientation of graphene on hexagonal boron nitride. Now this is a recent measurement. It's unpublished data, but it's very exciting. Recently, a discovery was made that you can use an AFM tip and apply an AC bias to the tip. And by applying an AC bias to the tip, you can actually cut graphene. Now, cutting graphene is actually really hard, and cutting it accurately is even harder. If you want to make nanoscale devices using bilayer graphene that have superconductor properties, you have to start by making those devices and cutting small flakes of graphene. And what was discovered is that an AFM tip is ideally suited to cut graphene. So you can use an AFM tip, apply an AC bias to the tip, use the software that is available on our AFMs to carefully control the piezos and make a certain pattern. So in this case, we wrote the letter CNS, which stands for Center for Nanoscale Systems at Harvard. And by writing the letter CNS and applying an AC bias, we were able to cut graphene into a specified shape. And the next step would be to lift this graphene and then use it to make devices. But this is a very nice demonstration of using an AFM tip to cut graphene. OK, so let's focus our talk on specific information about the instrument that is now available at UT Dallas for all the researchers. What is new about the instrument? What about the resolution of this machine? What kind of samples that you can put into this instrument? So this new instrument is called Jupiter. Jupiter is the largest planet, and this is a large sample AFM. So we chose the name to describe that this is a large sample AFM. And the letter XR stand for extended range. So the JupiterXR instrument has a very large XY scan range of 100 by 100 micron. And it's also a very high resolution instrument. So compared to conventional AFMs, where you have to either choose to work with a very small sample AFM to get high resolution, or if you work with a large sample AFM, you don't get very good resolution. JupiterXR is a new instrument that has both a large scan size, so you can go from 100 by 100 micron scan size down to say 10 by 10 nanometers. It has exceptional vertical resolution and XY resolution. So what are some of the specifications? So the Z noise of the instrument is less than 25 picometers. What that means is if you bring wafers that are very, very smooth and you wanted to measure roughness of those wafers, you will be able to get accurate results on these wafers or coupons or 2D materials, whatever you are working on. The example on the right is an epitaxial silicon wafer where the roughness is less than 80 picometers, and you can resolve each of these atomic planes in the AFM. And this kind of measurement can be done routinely in the instrument. And on the left is just a stretched out plastic bag, and you can see the molecular lamellae on this sample because the tip can maintain a very, very accurate control of the tip sample forces. So you can get accurate measurements on soft samples like plastics and on smooth and hard samples like silicon wafers. The instrument is fast, so it can frequently scan at scan rates in the range of 50 to 20 Hertz while maintaining very large scan sizes. So you will now be able to get lots of measurements quickly and not spend too much time in front of the AFM, and also get nice results without compromising on data quality. The example on the left bottom is CellGuard battery separator membrane. Imaged at 40 Hertz, you can still see a very nice high resolution image. In this measurement only took 13 seconds. And on the right is the edge of a razor blade where you can see a very large area, like 100 micron area imaged. And the polished razor blade at the nanoscale looks very, very rough. And the topography is on the order of about 500 nanometers. And we can measure a very large area, almost 100 microns, in just 65 seconds. So you can get good tracking at the nanoscale, you can get good tracking at the micron scale and get data fast. The other nice thing is the instrument is easy to learn and easy to set up. So there are several steps in doing an AFM measurement. And one of the steps is called laser alignment. Laser alignment means that if you have an AFM probe, you need to make sure that you put the laser that is required for doing the measurement at the right place on the cantilever. And in most conventional AFMs, there are several knobs that allow you to align the laser. The good news is that UT Dallas selected a very nice instrument where the laser alignment is automated, so your life is going to be easier. So I'm going to play a little video that shows how you perform laser alignment on Jupiter. So both the laser and detector alignment are motorized as it's shown in the video, and this will save you several minutes every time you walk up to the instrument to make AFM measurements. So you should definitely take advantage of this automation that's available in the instrument. So moving on to the next slide. This is also a large sample AFM. So it can accommodate samples as large as 210 millimeters. And also it can go from one end of the wafer to the other end very, very fast. So you can zip around on the sample, make measurements quickly, and get a lot of data quickly. Now this instrument is not just there to do large wafers. It can also make measurements on smaller samples. And there are smaller magnetic locations on the sample that can be used to place smaller samples. And you can set up like a small automation recipe where you can go from sample to sample and make measurements. It can also accommodate samples that are very tall. So the height of the sample can be up to 35 millimeters tall. So just to summarize, you can hold vacuum. You can hold the samples down either by vacuum, or you can hold them down magnetically at those 8 magnetic locations that are available. The vacuum comes in different rings, so if you have smaller coupons or larger wafers, depending on which vacuum ring you leave open, you can make measurement, or you can hold different size samples. The optics on this instrument is really nice, which means when you walk up to the instrument with your sample, you will be able to find the region of interest easily. So the optics has a resolution of around 1 micron, and this will really help you find your location of interest easily, bring the tip down on the surface and get high resolution images. The instrument can perform a variety of nanomechanical measurements. So if your research group works on mechanical properties of graphene or certain polymers, or if there are coatings on your semiconductor devices, you can accurately measure the stiffness or the adhesion of these surfaces. And there are several techniques that are built right into the machine, like AMFM viscoelastic mapping, contact resonance, bimodal dual AC. So we won't talk about each and every technique in detail. Maybe we can do this in another seminar at a later point where we go in depth into nanomechanical techniques if that's of interest. The short thing for you to remember is that if you want to measure mechanical properties of your materials at the nanoscale, those functions are available at UT Dallas now. And we also talked about electrical properties earlier in the seminar. So electrical properties can also be measured on this instrument using the different techniques that are shown on the screen, like electrostatic force microscopy, Kelvin probe force microscopy, and conductive AFM. The example on the left is carbon nanotubes in a polymer, where the nanotubes are embedded in the surface, but by performing a technique called electric force microscopy, we can visualize the location of these carbon nanotubes. They show up as red in the image. The example in the center is a transistor, where we are performing Kelvin probe force microscopy to measure the variation in the dopant profile. And the example on the right is a molecular layer of a polymer called melamine cyanurate on graphene. And conductive AFM shows the moire pattern and also the molecules of melamine cyanurate. So very high resolution images. And my last slide now, if you have more questions, you have amazing support. So at UT Dallas, you have this an awesome scientist responsible for the instrument, Dr. Audrey Hammack. She's a process engineer in the clean room. Asylum Research has Bob Newton, who is our regional sales manager. He also has a very strong technical background coming from the electrical and surface characterization field. And if you have more questions, technical questions, you can write to us at support@asylumresearch.com. So we hope you will, make the best use of the instrument. And as you use the instrument and you have questions, you can reach out to all of us. So thanks for attending the seminar today. I'd be happy to take questions.
Thank you, Mayur. You do have questions in the queue. The first question is, what is the time difference between the 512, I'm believing megapixels, it's M pixels, versus the 1024 pixels on page 6?
Excellent question. So the time difference is based on the number of lines. It is not based on how many points you save on one line. So when you take an AFM measurement, if you choose to have square pixels, which means you do 500 points along one line and you save 500 lines, the total time taken for the measurement is simply the number of lines divided by the scan rate. So to give you a simple example, if you are making a measurement in the AFM at say 1 Hertz, which is you scan each line in 1 second, then your measurement time would be 500 seconds. As you go from 500 lines to 1000 lines, your measurement time simply becomes twice as long. Now your measurement time does not change if you decide to save more pixels in the image. So I would suggest you should always save more pixels because you really don't pay a penalty for saving more pixels.
Thank you, and I believe that this next question relates to what you just explained, but due to the fact that I am not the subject matter expert, I will go ahead and share it with you. Does changing a pixel density vary your analysis time?
Again, good question. No, pixel density as you go from left to right does not change the amount of time it takes, but as you scan more lines, it will take longer to get data.
Thank you, Mayur. What is the difference between CAFM and STM?
That's a great question. So I'm going to go back a few slides. OK, so scanning tunneling microscopy was the first scanning probe technique developed. And in fact, that was the Nobel Prize back in the 80s. And the idea in scanning tunneling microscopy is that you have a sharp metal wire, and when you bring a metal wire close to a surface and you apply a DC bias between the two, before the wire touches the surface, a phenomena happens called tunneling, where some electrons from the surface, they go into the metal wire or the metal tip. And when you scan the surface line by line and you use the tunneling current as a feedback, that technique is called scanning tunneling microscopy. Now, STM has a major drawback, which is if your surface properties are changing or if you have different materials on the surface, they will show up as a difference in topography because the feedback is current or the tunneling current. In conductive AFM, what we are doing is we are feeding back as a regular AFM technique. So you are scanning the surface line by line and the feedback is like standard AFM feedback, but separately on the side, you are measuring the conductivity variation in the surface as an additional channel. So you are not relying upon the electrical signal as your feedback parameter. So your tracking on the surface is in standard AFM mode, but you are simultaneously measuring current. In STM, you are getting the surface topography using the current data. So the short answer is conductive AFM is a much more powerful and a reliable technique than STM. Now, the reason STM is still popular is because STM can get very high resolution, especially if you do it in ultra high vacuum. Now, the interesting thing is that recently on the Jupyter AFM system, we have been able to get STM quality conductive AFM data. So I'll show you a picture here real quick. So the image on the right is a conductive AFM image, and we are getting STM quality data. So I think more and more user groups are choosing conductive AFM over STM for doing ultra high resolution measurements.
Excellent. Is this equipment capable of measuring mechanical properties of thin film, specifically nano indentation of films of 100 to 500 nm films?
Yes. So the instrument has a measurement mode called force mapping. So depending on the amount of force that you want to apply on your films to measure their mechanical properties, the instrument is capable of performing indentation experiments. The difference between a standalone nano indentation instrument versus an atomic force microscope used for doing indentation experiment is that in a bulk nano indenter, the forces are usually much larger, but at the same time, you don't have to worry about a cantilever that flexes. So I don't know if you can see my video to the person who asked this question, but in an AFM, you have a cantilever that pushes into the surface and it flexes. In a nano indenter, you have a vertical diamond tip that comes down and pushes onto the sample. So data interpretation in a bulk nano indentation system is easier. However, in case of AFM, you are able to measure very thin films and get results where you don't have the effect of the substrate because the control of the tip sample forces is much more accurate than a bulk nano indenter. So the short answer is yes, you can use this AFM that's at UT Dallas to do indentation experiments on 100 to 500 nanometer films. And if mechanical measurements are of more interest, I'm happy to give another detailed talk on that topic.
Thank you. We have two more questions in the queue. The first one is, can we do a conductive AFM measurement in the AFM we have at UTD clean room?
The UTD clean room needs to purchase the conductive AFM tip holder. It's a relatively simple and an inexpensive upgrade. So short answer is no at the moment. Yes, if you acquire the conductive AFM tip holder. And if you send us a note or an email, I'm happy to talk about this in more detail. But you just need the conductive AFM tip holder to be able to make this measurement.
And the last question I have in the queue is, can you talk a little about what settings and AFM tip types and stiffness one should use to accurately measure surface roughness and adhesion properties of soft, dielectric, materials, for example, PDMS, will surface charging during scanning be an issue?
Great, that's a loaded question. I'm going to break it down into small bits. So if you're measuring soft samples like PDMS, it is important to choose the right measurement mode. That's number one. Number two, it is important to choose the right measurement technique. The right type of AFM probe. So the measurement mode would be contact mode versus tapping mode. Within tapping mode, you have to choose whether you are doing attractive tapping or repulsive tapping. The choice of probe is important, whether you choose a stiff probe or a soft probe. And then the type of measurement you wanted to do, you wanted to measure adhesion. So on the instrument that UT Dallas has, AM/FM viscoelastic mapping mode is the mode you would use to measure adhesion. The type of probe I would select would be something that's not too stiff. You may want to write this down. The probe is called FS1500. It stands for Fast Scanning 1500. FS1500 would be a nice probe for this measurement. And I would perform this measurement in tapping mode and make sure your parameters are set up so that you are applying a very small force between the tip and the sample, because PDMS is very soft. Now, to answer your question, will this charge your sample? It's possible. However, you can take care of this charging problem by appropriately grounding the tip and the sample. So the tip is usually at ground in an AFM tip holder. So we don't have to worry about the charging problems as much. And like with all the other questions, if you want additional details or you want us to help design your experiment, you can reach out to us and we'll be happy to help.
Thank you, Mayur. Of course, we do have just a few more questions in the queue. It appears that I glazed over one of them, so I want to make sure that I address that with you. It is, do Kelvin probe and conductive AFM use specialized AFM probes? Could you comment on types of probes available?
Good question. So for doing Kelvin probe microscopy measurement, you want to make sure that the probe has a high Q and a low K. So what I mean by that is the probe needs to have a high quality factor and a low spring constant. The lower the spring constant, the more sensitive your measurement is going to be. So you can use a probe called Asylum electrical probe that again, if you send us an email, I can give you a name of specific probes that you should use for the technique, but the choice of the probe will depend upon what kind of charges you are looking to measure on the surface, what kind of sample you have on which you want to perform KPFM. There are 2 or 3 different probe choices. Usually metal coated probes will work well. There are probes available that have a platinum coating on the tip side. Those will work well. The other thing to make sure is you set up the instrument in a way that you don't scratch that coating, because if you scratch that metal coating, then your KPFM data is going to change.
Thank you very much. And the final question for today's session is, what books are recommended for this instrument?
So AFM is a relatively new technique, and there are not many textbooks that are up to date in terms of explaining AFM in the most simple way to get you ready to make measurements. There are, however, a few good books out there. I don't remember exact titles. There was one book that talked about the physics of AFM and applications of AFM for polymer research. There is a book called AFM for biologists that also talks about the physics of AFM, but then goes into more details of biological applications. The best way to learn AFM is by we have training material as well that goes into more detail than what we did in this seminar, that talks about feedback loops and different measurement modes and selecting probes. That might be the best way. And As a hands-on technique, the other way would be to simply go to the instrument, try a simple experiment, and work your way through the software, get hands-on training from the staff at UT Dallas. They may have SOPs that they have written out that you can use. Once again, if you send me an email, I can send you a list of books that are good for learning AFM. The fastest way would be to simply jump right in and start making the measurements.
Thank you. And of course, I did have one additional question come across my radar, and I will officially say that this is the final one as we have reached our hour time mark, and we want to honor everyone's time and thank them for attending today. The question is, what signal is electrostatic mode measuring, and how different is it from Kelvin probe microscopy mode?
Great question. So EFM measures an electric field between the tip and the sample. KPFM is a very similar technique. The difference is that in KPFM there is a feedback loop that applies a DC bias to the tip to keep the difference between the DC bias on the tip and the charge on the sample zero. And so this feedback loop gives you a more accurate or a quantitative measurement of surface charges. EFM is an open loop technique that gives you a map of the electric field. So the short answer is, if you can do KPFM, do KPFM. It is a more quantitative technique, but it is a little bit more complex to set up. EFM is easier to set up, but it is less quantitative.
Very good. Well, thank you for sharing your time, talent, and resources with the attendees and community at large, Mayur. To obtain further information and a list of Office of Research events, please visit research.utdallas.edu and have a nice day.